Stanford University.
Lecture 2 of CS 193G. We're going to be talking about CUDA programming basics and GPU history. So what I'm going to kind of walk you through kind of step by step is first, basic kernels. You saw some of that, in the first lecture, but here I'm going to go kind of really, make sure everybody gets all the details. Then basic memory management, because we're talking about physically two different pieces of hardware, the GPU and the CPU with its main memory. You have to do memory copies to and from the GPU explicitly. And then lastly, how do you coordinate stuff executing on the CPU and on the GPU? And obviously, I can't cover every nook and cranny and every special case. So if you have more questions, ask or come ask after class. But for all the details, you obviously have to look at the programming guide, which is up on the web. All right, so basic kernels and execution. As we said, kind of at a high level, the CUDA programming model is that you have a parallel code, which is described in a kernel, and that is launched from the CPU, and that command to execute that kernel with certain data on a certain size grid is sent to the GPU. There is extra software which hides all the details of how that is done. And then there's dedicated hardware on the GPU which receives those commands and then broadcasts all that information out to all the many cores on the GPU. They tells them to start executing and make sure that they all finish. And when they all finish, it notifies the CPU back, hey, I'm all done. And then the CPU, through the CUDA runtime, then kind of knows that and can continue onwards. As we also pointed out a little bit, launches are hierarchical. You don't launch a flat grid of thread. You launch a grid of thread blocks. And thread blocks are not that small number of threads which can cooperate and communicate. Kind of for the first couple of lectures, you just have to declare thread blocks and you won't have to worry about the details. And we'll go into what that actually means and how they can actually cooperate and communicate later on. And you can obviously have multiple kernels in your copy, many, and you can actually also launch them before the other one is finished. They will just naturally queue one behind the other. And actually on the newest hardware on Fermi, if one of them is done or it doesn't fill up the whole chip and you do everything exactly right, they can actually be executing multiple kernels at the same time on the GPU so that you can make maximum use even though you're having kind of smaller tasks. So the code should be pretty much familiar to you. It's just going to be C with extension. Kind of, you saw one example in the first lecture. And then you have these new automatic variables, the thread ID and block ID. All right, so I've been staring at this text for too long. Let's show you pictures. So the CPU, kind of shown off here on the side, will launch a grid or a kernel working on a grid onto the GPU. And that is we described in the first lecture. The GPU is a many-core processor. So each of these small green boxes here represents one core. And then there's dedicated hardware, not shown here. It's tiny. It basically tells all of them that, hey, here's some work for you to do. Here's your input. Here's where the output should go. Here's some more configuration state. Everybody ready? Go. And then it makes sure. Too loud?
No, your microphone.
It's off.
No, your microphone.
Oh, no, no.
Sorry.
Vectoring too big or
something. That's right. Too much hand gesturing. So, this is a bit of. And then this little piece of hardware will check as the whole grid executes. And when it's all done, then it will say, OK, here's some more, when the next kernel is ready, here's some more work. And again, you will have to worry about none of those details. So the programming model is serial. So you're just going to write the kernel code as normal serial code. Jared showed you some example code in the first lecture. And you basically, the only extra thing you have to know is where are you in the grid and where are you in the thread block. All the other things about who else is executing, you don't have to care about that unless you want to communicate. And so the thread just looks like a normal CPU thread. You have registers, you have memory, you execute on stuff which is in registers and you load and store from memory. The kind of new abstraction, this kind of the cooperating block, the thread block, is such that we guarantee that thread blocks, all the threads in that thread block will be executing at once. As Jared mentioned the first time through, the grid can be larger than the physical resources. So CUDA kind of virtualizes those resources. And so that it doesn't matter if you execute on a very tiny GPU, something which is in a notebook, or even in the future in a cell phone, or on the biggest GPU we have, or even bigger one in 5 years down the road. The code will, the same code will run exactly the same, and will hopefully get, a speed up just naturally from going to bigger GPUs. But that means that you have no idea which other thread blocks, which other threads are active at any given point in time. And this is kind of like one of the core concepts. Since you don't know who else is active, you can't say, oh, I'm just going to wait for thread X to give me something, and then I'm going to take that result and work on it some more. That thread block and a thread in a thread block might have executed before you, might be executing right now, or might execute a long time after you're done. So basically, there's no guarantee who's active except those threads who are in the same thread block as you are. What physically happens is that a thread block gets put on this piece of hardware, which Jared described the first time, called a streaming multiprocessor. So that's a whole bunch of little throughput cores together with a dedicated piece of memory called shared memory. And through that, you can communicate and coordinate. And so now you have two different kinds of memory. You have normal memory, which we'll call global memory. And we have shared memory, which is private to each individual thread block. So the values one thread block puts in, the next thread block won't see. And so basically, every time you want to put something in shared memory, you have to specifically put it there and specifically take it from something which is in shared memory. No. Streaming multiprocessor is something physical which is in silicon. It's a group of small throughput cores together with other stuff which share hardware. Thread block is a programming abstraction, basically a group of threads which are executing at the same time and are executing on one SM. Actually, it's not a given that only one thread block is executing on one SM. There actually can be multiple. It depends on lots of things. But you're guaranteed that all of those threads in a thread block are on that SM, and hence they can communicate and coordinate. Another question?
How is that possible? I mean, we've seen that we just say how many threads you want in a thread block.
Mm-hmm.
So what happens if you keep increasing that number? I mean, there's a limited number of cores.
Right. So that's right. So there are limits on how large you can make thread blocks, and those are related to how much the physical hardware can support. And no, basically the number of threads. The smaller cards have fewer streaming multiprocessors, but each streaming multiprocessor supports has the same number of cores. Somebody's going to break through the wall. So they have the same number of physical cores, the same amount of shared memory. It's only that bigger cards have more of these streaming multiprocessors. But you can always guarantee that, even if you have a max size thread block, even the smallest GPU will be able to execute at least one at a time. And bigger ones will be able to execute a lot more.
Shared memory.
Can you repeat the question?
So what about the size of the shared memory size?
Right. So the shared memory is a finite resource. On kind of the previous generation of cards, the Tesla generation, it was 16 kilobytes. On the cards which we just launched, the Fermis, they can be up to 48 kilobytes. And so you can request how much shared memory you want. You can be anywhere from 0 to up to 48 kilobytes. And you have to tell the runtime and the hardware up front how much you will want, because if somebody suddenly, while it's running, asks for more shared memory and it's already used up, we'd be in a bad spot. Another question.
Shared memory is dedicated to a given thread block. It's not shared among thread blocks.
It can be allocated to multiple thread blocks if any given thread block doesn't need all of it. But one thread block will never see the values, they'll never see what's going on around it. So you don't have to worry about, how many other thread blocks are active on that shared multiprocessor at any given point, a streaming multiprocessor, at any given point in time. Other question? All right. So again, we just have these two different memory spaces, shared memory and kind of normal memory, which is we usually call global memory. So when you launch a grid, you say, I want to have thread blocks of size so-and-so, and I want to have this many of them. Then, they get distributed among all the streaming multiprocessors which are on the card you just happen to have in that computer, and start to execute. And if the grid is larger than the number of physical streaming multiprocessors, then there's dedicated hardware to kind of sequence through the thread blocks. But the order is arbitrary. You can depend on a lot of things, runtime behavior, generation of the card, so on and so forth. So you cannot depend on any given order of thread block execution. So again, for communication and synchronization, you have to do that within a given thread block. The other thing you can do, obviously, is when the grid finishes, when the kernel finishes its launch, all the data has been written back, and then everything is, quiescent, and then you can launch a new kernel, and that, obviously, there you can read, again, arbitrary data from anywhere in global memory. So the result of any thread from a prior kernel launch can now be read by anybody, and so you can do communication in that way. Right. I seem to be running ahead of myself here. So the other thing I should mention is that, again, kernels, within a kernel, everybody can look at all of and touch all of global memory. And because there's no given ordering, right, if you just happen to compute the same output address for different threads, they will, happily pile on top of each other. And since the ordering is not guaranteed, you have no idea which thread's result will finally end up, being in global memory when everything is done. So if you want to you want to pre-compute and think about where each result should go, and if you then need to communicate, that result to somewhere else, then for the first approximation, you need to launch the new kernel. The other option here, again, is to communicate inside of a thread block through shared memory. And we'll be going into that in lectures 4, I want to say. So I alluded to this a little bit at the beginning. Physically, the GPU has its own memory, which is smaller in size, usually, than what you have on the CPU side for normal, what we call host memory, but is much faster. So in the first lecture, you saw some bandwidth numbers where bandwidth from the GPU was about 10x or more that the CPU. And that's because we physically have a separate pool of memory, which is, much more, per unit is much more expensive and much higher speed. And so to get, your input data from the CPU, from whatever your program is doing, ready to be executed on the GPU, you need to tell explicitly, hey, here's some data. I want to copy it over to the GPU. And when you're done, you need to explicitly copy it back to the CPU. And you'll see that this is basically exactly the same kind of mem copies, very similar syntax as what you're used to if you're programming C. And you can also, of course, this is kind of the device, what's trying to point out here, you can have multiple GPUs in, the same PC. And you can actually, be talking to each of them and have each of them working on separate things and copy different pieces of data to each of them too. All right. So let's go back to kind of the example that Jared was showing in the first lecture. So here, you just want to add two big arrays, A and B. And so he kind of already mentioned the syntax, but let me just go over it again. You have a new keyword global with which you decorate a function. And that tells the system, hey, this is a function which will be executing on the GPU. So don't compile it, for whatever your CPU is, usually x86. Compile it so that the GPU can understand it and can execute it. And when you put it, when you write code like this, and then you pass it to the CUDA compiler, NVCC, and compile, it will do exactly that. You will not be able to execute vecadd on the CPU, but you will be able to execute it on the GPU. So that's the first keyword. That's crucial. Question?
Do you know if the why
It's.
I don't know.
So I don't know. I've wondered it myself. So CUDA sort of came out of a project from Stanford called Brook, and they actually did use the word kernel to sort of tag their kernels. One thing about kernel is it's a little too general a word, because you could think of kernels like global functions can't talk to each other, or threads can't necessarily talk to each other that are in different blocks, but you could imagine certain kind of kernels that would make that possible. So as a language designer, I might want to reserve the word kernel to mean something more general. But I'll try to find out where the word global came from for next time.
Okay. So global is the first keyword. You have to prepend it to any function that you want to have run on the GPU and be callable from the CPU side. Jared mentioned there's another keyword, device. Those are functions which run on the GPU but can't be called from the CPU. So if you want to, call functions within a global function, for those functions you'll have to add device in front of them. And again, the compiler will figure out the right thing to do. So that's the first keyword. The next keywords are these automatic variables, thread IDX, block IDX, and here block dim. And so if you're compiling for the GPU, and this is a global function or also a device function, those are automatically present, and you can always have access to them. And they basically tell you which thread block am I in the whole grid, and within that thread block, which thread am I. So if you want to get your global ID and you have a simple kind of 1D thread block and grid, you can do what is shown here and say, well, the block is, again, a new variable kind of magically appears, block dim. The block is so big, I am such and such in the whole grid, and then you add my thread ID, and that is my global index. So you'll note again that these .x, 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 and those indicate that these are not just simple scalars, but they're actually tuples. And so blocks can actually be anywhere from 1 to 3 dimensional. You can configure that. So if your application naturally maps to a 2D grid or a 3D grid, and it's just easier for you to think about it like that, then you can say, I want to have a 3D thread block, you know, tell the runtime that, and you'll get thread ID, you know, x going from somewhere to somewhere, from 0 to some number, and the same for thread ID x dot y and thread ID x dot z. But you don't have to. This is, you know, real clear. The other thing you need to consider is, so I mentioned there's a maximum number for the thread block size, the number of threads per thread block. Currently, that's 512 threads per thread block, and that number doesn't change no matter if it's a 1D thread block, a 2D, or a 3D thread block. So just be aware of that. You can't make your thread block bigger by going into more dimensions. Some people assume that. The same is true, the same thing that you can have multidimensional grids as well as thread blocks. So block ID, you know, you have block ID x dot x there, but you can also have dot y. And while you can have dot z, currently, actually, you're restricted. Even though it's a 3-tuple, you're currently restricted to only have 2D grids. And so z will always be, you know, 0 or 1. And so now that, you know, so this looks like a normal function. What else do you need to do? Well, if you're writing, you know, normal little C program, you'll have your int main. And so you say, okay, I've told the compiler this function should execute on the GPU. So I'll just call it, but, you know, pass it some input arguments. We'll get to what those input arguments are and how you make them work in a second. But the crucial thing here, another bit of new syntax here, are these triple chevrons. And this basically tells the compiler again, hey, this is an invocation, run this on the GPU now. And the two numbers here are the number of thread blocks for a 1D grid and the size of the thread block. So in this case, we have a vector of length n, which, you know, hopefully is an exact multiple of 256. And so to, you know, add every single element of vector A to B, we say, well, we need n divided by 256 thread blocks, each of which has 256 threads. Any questions up to there? All right, that's pretty simple. Question? Right. So basically, the choice of thread block size, it has some performance implications depending on your code. For code like this, it basically doesn't matter. For more complicated code, it might matter, and we'll go into that in later lectures. All right, so okay, we've told the compiler and basically the runtime, hey, launch this function on the GPU, and here's your input. So, but I just said you have to explicitly copy stuff over to the GPU before, you know, you can work on it. So what are all these DA, DB, and DC? So you have to do some work before you get to what we call the kernel launch, before you invoke the function which is going to run on the GPU with its input argument. So here, kind of for simplicity, we assume you have the vectors A, B, and C in some form already on the CPU, you know, just from your program. And so now you want to work on the values that they contain basically on the GPU. So what you need to do is you need to allocate that memory just as you would in a normal C program. But in this case, you need to allocate it for the GPU. So instead of calling malloc, you call CUDA malloc, and it has, you know, it looks slightly differently than normal malloc. It doesn't return a void pointer which you then cast to whatever you need. You basically pass it, you know, pointer to a pointer, a void star star, and the size. So the size again is just in bytes, the same way as for normal malloc. It's just that you pass it directly to pointer where it's going to, you know, put the base pointer basically in. And it, again, different from malloc, actually returns a specific error code. If you want to look at the details, Jared has written up a tutorial basically on, how to check for errors and other things. So this is a little bit simplified. If you want to have robust code, after these CUDA mallocs, you would check, the same way as you do with malloc. Hey, did everything work? Did all my memory allocations work out? If yes, I can proceed. If not, I ran out of memory, something else bad happened. Need to abort or need to try again or something. So after you've malloc, and again, slightly different syntax, you say, okay, I now have all this memory allocated on the GPU. So I need to copy. Now I actually need to do the copy. And so now instead of memcopy, which again is normal C, you have CUDA memcopy. And again, it looks a little bit different than normal memcopy. It's basically amount of data you want to copy, starting from where to where. And because CUDA memcopy isn't just from one place in the CPU's memory to another place, you need to tell it explicitly what you want to do. So here you need to tell it, hey, this memory is on the host, is on the CPU side, and I'm going to copy it to the GPU, which so we call that copy to device. And again, you do that for all your inputs. And again, for robustness, you want to check that that worked out. Here we're assuming that worked out. And note here that, your pointers, right, they're just normal C pointers, or so they seem. But the pointers that you pass to CUDA malloc now point to somewhere in GPU memory. So if you wanted to dereference them on the CPU, I can basically guarantee you that, you would crash right away, because it's, basically like having two phone numbers without the country code, and you don't know if you want to call somebody in the US versus somebody in Japan, and you get somebody the wrong number, or the wrong person, basically. So you have to be very aware of, what are these pointers pointing to, and in what memory space are they pointing to something. So kind of, simplify people's lives. We kind of have this convention, which at least basically through the, first couple of machine problems, and also on these slides, to denote things, array pointers and arrays and other structures, which are on the CPU side with a, H underscore before, and prepend D underscore for things which are on the GPU for device pointers. Question?
So what happens when you have two devices?
So if you have two devices, there is many more API calls, which are not shown here, where you have to tell the runtime, hey, right now I want to talk to GPU 0 or 1 or 2 or 3, and it will then do appropriately. So at any given point, you're just copying to one GPU or copying back from one GPU, no broadcast. All right, so this is basically all the work you have to do before, you have to use this little bit of syntax, the triple chevron, and basically execute something on the GPU. And note again kind of what happens when you do the final step. You do vec add. It's basically that the CUDA runtime on the CPU recognizes you want to execute something on the GPU, packages up all the inputs and the grid size and all the object configurations, sends it over to the GPU. On the GPU, dedicated piece of hardware says, aha, I have new work, basically broadcasts information to all the little cores which are on there, starts execution, sequences through your grid if it's bigger than the physical GPU, checks for errors, and it returns an error code if something went wrong, and informs you when the whole thing is done. So that all happens behind the scenes. You just know it's done, it went very fast. And so now, you want to get your results back. So what do? You again call CUDA memcopy, and this time you just you invert the direction. So this time you're copying from the device, so thus DC is here, to the host, and you tell it copy device to host, not host to device, and it will copy to the CPU's memory. So a little thing I should note here, which is kind of we haven't put in for simplicity, is that actually what happens is when you call vec_add, that command gets sent to the GPU, but you immediately can continue to execute on the CPU. You don't block waiting for the GPU to finish. Because depending on, the size of the grid and the amount of work you're doing per thread, I mean, that might take some time. You don't want to block the CPU for that long. So if you so really what you want to do is add a CUDA synchronize there, which makes sure, basically says, wake me up when, the previous kernel was done. You don't need to do that in this case because basically if you do a CUDA mem copy, that basically puts that in automatically. But in other cases, you might need to do that. So just that for completeness. All right, so you have your result. You're happy with it, hopefully, and you continue on your merry way. You should, and you need to, free stuff on the GPU just as much as you're doing it on the CPU. So here again, you have CUDA free instead of free, but nothing else changes. And by the way, please don't call CUDA free again on some CPU pointers, because it will throw an error and you will crash. So we've shown you one example of what you can do, just to play with these automatic variables and kind of to show you what you would get. Here's some examples. These might be a little small. Hopefully everybody can see them in the back. So if you just want to copy a constant, for example, into a huge chunk of memory, which you then want to use further on the GPU, right? You can do that. You basically still need to compute your overall global index so that every element of the array gets its output, but it will all be constant, right? There's no need to copy something from somewhere, obviously. If you want to see, in your output, how that yes, indeed, my thread blocks are of a certain size, here of size 4, then you basically just, for example, can copy your block ID into your output, and then all the threads looped inside the same block will have exactly the same output. So here you see thread blocks are of size 4, and so you get this pattern. And finally, the thread ID is not unique globally. It is just unique in a thread block. So if you just copy a thread ID into your output, you'll get this repeating pattern. And this is again a reminder that if you want to have your global ID, you need to look at both your block ID and your thread ID, or else you'll be reading exactly from the same spot and writing from exactly the same spot for every thread block in the whole grid. So again, this is kind of just to summarize and some more details. If you write something, some code and have some access through some array or you reference some pointer in a function which is global or device, you can only access stuff which is on the GPU. This is kind of the inverse of what I said. Don't dereference device pointers or GPU pointers on the CPU. Don't dereference CPU pointers on the GPU because, again, you will crash. A slight difference from kind of generic C functions is you can't have a variable number of arguments. This is basically because the runtime wants to pre-allocate certain buffer sizes and stuff like that and know how much needs to copy over. No static variables, no recursion. This is kind of the bigger one. So if, as I said previously, in a device function, in a global function, if you want to call another function, it needs to have device in front of it. But you can't, inside of a device function, keep calling itself, down and down and down. And that's basically because, think of it, this is a massively parallel processor. So you have tons of threads executing. And so each of them needs more and more and more stack space. And you don't know how much stack space they'll need. There's no good way for the hardware or software to keep giving all the threads more stack space at any kind of reasonable speed. So no recursion. And no dynamic polymorphism. So again, this is kind of just reiterating what I've said a couple of times now and what Jared said in the first lecture. Functions with which you prepend global can be launched from the CPU onto the GPU. Global functions can call themselves. If you want to call something within a global function, it needs to have device in front of it. And stuff which you want to have compiled both for the CPU and the GPU. Let's say you have a small helper function which is a bounce check or something. You want to prepend both host and device in front of it. And that basically tells the compiler, hey, compile one version for the GPU and one version for the CPU. And so those two things don't conflict. You can add host and device and compiler won't complain. It's not an either or. It's an you can have it's an and. You can have both. And another small detail which Jared mentioned the first time. Global functions must return void. It's simply the fact that if you have 1,000,000 threads and you return int, which int should you be returning? There's no good kind of argument there. So global functions have to be void, and you should put your output, in an array or some other structure somewhere. So, running ahead of myself. So this is just again reiterating. You need to explicitly copy stuff to the GPU and from the GPU. And again, please don't dereference GPU pointers on the CPU and vice versa. So the one little thing, another function which has a CUDA analog is memset. So this time, instead of having a void star star, it just wants the pointer and value and size again in bytes. So very similar to normal memset. And CUDA malloc, as I said, takes arguments, size of the structure you want in bytes, and it wants a void star star pointer. So if you just have a normal pointer, dereference it once and cast it to a void star star. Okay, I think we can skip this. So I've kind of shown it to you in pieces. Here we're just going to do a very quick walkthrough of exactly kind of the same code, what you should be writing. If you have some array A on the CPU and you want to work on it on the GPU, have a pointer which it's a device pointer. So for example, you can prepend the underscore, but choose your own kind of standard. Then alloc it, malloc it both on the CPU and the GPU. So here we're actually adding, okay, do check if malloc actually succeeded, which we didn't have in a simplified example before. And in this example, we just fill the array on the GPU side with 0. Not very exciting, but still. And so we then copy it back to the GPU. This is, again, a little small for people in the back. I apologize. So if you just want to do, fill huge arrays with a number, right, you can do it this way. You don't even need to call a trivial kernel if you don't want to do so. And again, the CUDA memcopy syntax, which I think I've explained enough at this point. And again, please free your pointers. I know some people just expect the OS to clean up after them. Not very good practice. So after having walked you through vector add, element-wise vector addition kind of 3 times by now, let's show you something a little bit different, which is shuffling data. Ooh. The idea here is you have some array, and you have basically let's say, reordered it. So for each element, you want to put it somewhere else. And you want to do this in a massively parallel fashion, basically taking advantage of the massive bandwidth of the GPU. So you basically have the new locations stored in the array indices, and you want to copy from previous array to new array. And what we're trying to kind of point out here is you don't need to do straight access. Every thread accesses exactly the neighboring element of the thread prior to it. You can access any portion of global memory, both for read and for write, and you can, do as many indirection lookups as you need to. You can have linked lists, trees, hash tables, what you want, and it will all work. No, there's absolutely no problem. The thing you have to think about in this case is actually the values in the array indices, because if indices I and indices j just happen to have the same value, then threads I and j will copy two values in the same slot, and you don't know which one will end up there. So you need to think about that, but you don't need to think about, can I access any part of memory, because you can from any thread anywhere to global memory, and the same thing for write. Question?
So if one thread reads a value from allocation memory, modifies it, and then writes to it, will that break? How can I make sure that it works?
So if you have, let's say, one element in an array, only you are reading, and then you want to later write to it when you're done, is that correct?
So say I have a counter, say I have a 128 hashes,
Sure.
and I have a bunch of things, and I want to hash. I want to see how many of each do I have. So I could have 7 elements that hash to the first
Sure.
byte. So what I would do is read the number that was on the first array, increment it, and then write it again.
Right. So that's a real good question. So what will happen is you'll get some really funky behavior. And the reason here is basically somebody might read the value, let's say 0, which is in it first, say, okay, +1, and then write it back out. And so it thinks, okay, I'm just alone in writing back, but at the same time, let's say 100 other threads also read 0. They all also calculated +1. And so 100 threads want to write back 1. So instead of getting back 100, you'll get back 1. Because the ordering is not in any way specified, you can't assume that thread 0 will have read, modified, and then written back some value when thread x, before thread x comes along, if x is later, so to speak. Because it could be the same time, it could be earlier, it could be later. We'll be talking about actually in the next lecture how you solve exactly that problem. And there's this thing called atomic instructions, where atomic just means uninterruptible, and where one thread can do an update to memory location and be sure that nothing changes while it's doing that. And we'll talk about that on Tuesday. Other questions? All right. So this is, again, something I alluded to here kind of in graphical fashion. Thread blocks can be one-dimensional, two-dimensional, or three-dimensional. You just need to tell the runtime which. For the syntax, actually, I think we have one tutorial entry on that on the 2D page, right? Yeah. So you'll see how to do that there, and you can check the programming guide if you want all the details. And so the grid itself, even though it's also kind of specified by 3 tuple, can only be two-dimensional at this point. And something else I should mention, let me just go back here. So up to this point, we've only ever shown you, okay, we invoke one function with a certain grid size, and that's it. Well, those two things are not, statically coupled at all. You can invoke the function later on with a totally different grid size, and it will run on, a subset of the same input if you give it the same argument. Obviously, if you give it different arguments, it will compute something, totally different again. So if you have small matrices, large matrices, intermediate sized matrices. You can always call the same function, matrix small or what have you, on them, and you just tell it, okay, here I want a smaller grid, here I want a larger grid, and it, will execute the appropriate amount. So basically, the grid size is just another input which you can dynamically vary, depending on your needs of your input and your other runtime requirements. Hope that's clear to everybody. So yeah, because we talked so much about 2D indexing, here's a small example. If you've declared your thread block or your grid in this, well, both your grid and your thread block in this case, to be two-dimensional, then block dim y and block idx dot y, will have values different from just 1, and the same for thread idx. And so if you're working, let's say, on a picture, right, it's very natural to say I'm going to be working on blocks of pixels. Then in this case, like you can calculate where you are in this two-dimensional image, right? Very simply, and it hopefully simplifies you're thinking about what your thread is doing and where it is in kind of the global space. Yeah. So here we're showing again how to exactly do this, but I think this is way too small for anybody in the back to see. So I'll refer you to the tutorial online, because then you can actually read it. So I think I've mentioned this like 3 times now, but let me mention it kind of on a slide in big block letters. Blocks must be independent. You don't know in what order they're going to be executing. So you don't know if somebody, even though their block ID might be 0 and yours might be 9 million, has actually finished by the time you come along and start executing. So if you are expecting some values to be there from block 0 or from any block, with any specific relationship, you will probably be disappointed. Most likely you will be disappointed. So you shouldn't expect some values to be there. You shouldn't spin lock waiting on some values from a specific block to show up, because you might be waiting for a very long time. Because, for example, if you have a small GPU, which only executes 1 thread block at a time, right? You might be spinning waiting for somebody to arrive, and they can never arrive because you're blocking everybody else. So communication can happen again between threads in a thread block, and between between subsequent kernel launches. Everybody's written back their value. The kernel is finished. You know everybody's done. That's an ordering that, say, a huge barrier between kernel 0 and kernel 1, and then you can assume the values will be there. And yeah, kind of the worst kind of example here is a shared lock. Everybody trying to grab it. That's kind of more of the synchronization side. If let's say in the case of GTX 280, 30,000 threads can be active at any given point. If you have one shared lock, everybody needs to grab it or tries to grab it. Guess what? You will time out. You will never get anywhere. So do think about how do you want to decompose not just your execution, but obviously you also need to decompose your data and your data structures for them to be parallel. Because if you just say, I have a tree which is guarded by a single lock, and I'm just going to do 30,000 parallel updates to it, guess what? You have just not changed anything. You've just made things worse. So think about parallelizing your data and your data structures, not just your execution. Those things go hand in hand. And if you do that, again, then you can say, I'm going to execute from anywhere from the smallest GPU to the largest GPU. And on future GPUs, which might be even larger or more capable in some sense. All right. With that, anybody has questions on this part? No? Too much information too fast, or too little information too slow? Bit of both. Okay, so I'm going to go into GPU history next and kind of try to explain to you kind of what the internal logic was at a very high level, why GPUs came to be kind of these general purpose, many core throughput computers. Jared went into that from the kind of Moore's law perspective, but there were very good internal reasons. But before I go there, again, at this point, hopefully you have looked at tutorials. That's MP0, and we're assigning MP1 like now. It will be due 1 week from today, Thursday at midnight, and it's up on the site. And so take a look at it and get working on that. All right. So with that, the second part, and I have 20 minutes. So the history of GPUs. So Jared showed you some graphs on Tuesday that basically GPUs started out as having roughly equivalent number of gigaflops as CPUs the far distant past, aka 10 years ago, and same for bandwidth, and they've just miraculously grown. And they kind of explain to you the high-level reason that GPUs are all about parallel throughput computing, and thus could take more efficient use, make more efficient use of Moore's law as opposed to CPUs. But so for those of you who used GPUs in the past or know a little bit, they started out not being general purpose throughput computers. Sorry, was there? Kind of how did we end up here from the GPU side? So GPUs are graphics processing units, or people used to call them video cards. That's the whole board, GPU plus DRAM plus other stuff. Why are they built? Well, to make images like this. This is not a photograph. This is a rendered image. This is a really nice ball dude that Jared was pointing out last time. And so just to point out some little things, I am by far not a graphics expert, but you can see this is all rendered. So all the little details of the skin are rendered, the shadows from the eyebrows and from the nose and everything are perfect. And maybe there's even a little bit of light kind of shining through the very thin pieces of the ear, very little bit. And so, believe you me when I say this is really complex math and lots of data movement to get one picture like this. And to get pictures like this basically in video games was the driving force, to make GPUs better and better and faster and faster. So what do you do? How do you go there? Well, the real thing, kind of what the graphic people tell you, there's lots of algorithms, very nice algorithms you have to invent. And you have to do lots of hacks, squeeze the most out of it, do lots of shortcuts. But for our purposes, the last bullet point is the most important. You basically go back to the graphics guys every year and say, more, 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 more. So that's what they did. And basically, GPUs started out, just for graphics. And graphics has this very fundamental abstraction called the graphics pipeline. And this started back in, I want to say the early 90s with OpenGL. Not if you're right. And so you have different stages through which your graphics primitives flow. And so at the top, you have things like triangles and vertices and attribute lists and all kinds of math stuff, lots of little matrices. And at the bottom here, when you're all done, you have a beautiful picture. And if you're running a video game, then let's say 30 times a second or 60 times a second, that picture gets sent to your screen, and you see that the monsters move this much closer, so you need to do something. But this pipeline is basically doing very specific things. It's fixed function, right? It basically started out as being, we can only do very specific things, the triangles, but the triangles in the end get formed into, colored pixels, and those colored pixels end up in very specific spots in memory, and that memory then gets sent off to the monitor. That's how GPU started out. And so what happens here at a kind of 30,000 feet view is basically triangles come in. You say, all right, this triangle, I'm giving you the coordinates for this triangle in some coordinate system. But since the player moves around, zooms in, zooms out, how it's going to actually appear on the screen is a different coordinate system, kind of what they call screen space. So there's a first kind of coordinate transformation going from, let's say, the coordinate system your level is in to whatever is your screen space. And then once you figure out, all right, so this is the coordinates of that triangle, relative to the screen, you go and you rasterize. And skipping one step here. So rasterization, let's ignore setup for one point. But rasterization is a very crucial step of saying, I have a triangle, which part of the screen are actually covered? For each pixel, I have to say, is this pixel covered by this triangle? If so, which part of the triangle? And so there's fixed function hardware called the rasterizer, which figured this out. There's lots of math. Has to be really high performance. Thankfully, it's also really good at taking advantage of Moore's law. Once you figure it out, all right, this triangle will actually cover half of the screen. I'm going to tell you exactly which pixels on the screen are going to be covered. You go to what's called texturing and pixel shading. And this is basically, you can think of it as each triangle has a picture painted onto it, and since that picture was off stored somewhere, and now you've transformed the triangle into this funky view, which is specific to this frame, and you've said, well, these pixels make up this triangle or part of this triangle. You want to say for each pixel, which part of that image mapped to that pixel. And so that's called texturing. And kind of the more advanced form, when you're doing more math, kind of figuring out how shiny is it, dark, light, other stuff, is called pixel shading. And so something else that the rasterizer did was basically compute the distance, basically simplified the distance from the screen, right? Is this pixel far or near to the screen? And this, for simple graphics, basically, everything is solid. So if something is closer to you, then that's the only thing you see. You don't see what's behind it. There's no transparencies. Again, for simple graphics. And so for each pixel, you don't just get a color, you also get basically how far, a depth value, basically how far away from the screen is it. And for purpose of this class, let's assume that if your depth is smaller, you're closer to the screen. And so what happens next is you skip ahead. Actually, there should be one more animation there. So what happens then with this thing called depth test and blending is, say, it asks the question, was there something previously at that pixel? If yes, is it further away or closer than what this pixel I'm currently having? If the pixel coming down the pipe is closer, then I'm going to override what is there and write in the new depth and the new color. And if not, I'm just going to throw it away. All that work was for nothing. And then so once that test is done, you write it back out to the memory, and you continue on your way, and you do this millions and millions of times a second, and you make the player happy by showing them the monster advancing on them or whatnot. So the thing what you have to note here is that at any point in this pipeline, the programmer is only thinking about one object, one pixel, or one vertex, which is part of a triangle, or the one triangle. You have to think about basically again what's going on around you, how many triangles are, what shape they are in, how big is the GPU. All that stuff is completely hidden from you by the hardware and by the API, and so that makes programming easy. And so even though there's massive amounts of parallelism in there, because of the structure of the API, only think about one thing at a time, because of the pipeline and because of some other things in the API, you don't have to think about ordering constraints and how these things communicate at all. Programming for graphics is easy compared to basically any other massive programming model for massive parallelism. And so that means you can work on all of these things kind of independently, and as the hardware gets better, it just naturally gets faster. You don't have to rethink your algorithms every time through, which, believe you me, if you have other things like MPI or OpenMP, you go to the next bigger supercomputer, you probably have to retune or rethink your whole algorithm because something's changed. So these boxes kind of in the past, when we had many fewer transistors represented one chip by themselves, and they just, data flowed from one to another. But kind of as things progressed, several things happened. One, we actually had enough transistors to put them all on a single chip. That's when, you got a GPU. It could do everything without having to do intermediate copies. But the other thing is, it's not just good enough for the graphics to get faster and faster and faster, right? You want to make it better and prettier. For those of you who have played video games, you will note that video games from 1990 are not quite as pretty as video games from today. But that doesn't happen just from going faster. It also happens from adding new and new functionality. So basically, I said everything right now was fixed mode. So basically, they added new and new modes. With every new release, there were 5 new modes here, 10 new modes there. You could switch something in the vertex stage. You could switch something else in the blend stage. And you just got this exponential explosion in terms of the number of combinations. And all of these different modes, a lot of them shared hardware, but some of them also kind of required their own thing. So you had all this hardware for these special modes, which most of the time wasn't used and was just enabled if a particular game or application needed that particular feature, which was just happens to be the newest thing. And if you guessed wrong what was going to be popular or what was going to be used at all, some piece of hardware, part of your chip, could be sitting there doing nothing forever, which is a huge waste, and you don't want to waste silicon like that. And the other thing was they just got tired of listening to game developers coming back, well, I want this and I want that. I want a pony. No, I want a dragon. No, I want whatever, right? They just wanted more and more features, and basically you can't give everybody everything. So instead of just giving them more and more modes, kind of, again, which just limited you what you could do, they started to make the pipeline or parts of the pipeline programmable. So it basically started out as, hey, we're going to give you this very limited set of instructions and very limited set of registers, and go do off and write your own programs and do your own thing. Don't come bother us every year for more things. Now you can actually go do whatever your imagination can come up with within very specific limits. So in the beginning, these were things which operated on 8-bit values or 16-bit values, not the normal 32-bit values that you're used to kind of from CPUs. Very restricted data types and very restricted number of instructions. So for example, you couldn't do if statements. You certainly couldn't do arbitrary loads and stores. You could only take your inputs from some very specific places. The length of your program was limited. At first it was like, you can't have more than 32 instructions in assembly in your program. Go do the best you can, right? And then it went from 32 to 128 and kept on growing. And you also had a very restricted kind of set of registers. And if you wanted to loop, it had to be kind of static looping. You had to tell the compiler exactly how many loop iterations you wanted to do. And again, no branching inside of the loop so that the compiler could statically unroll it. So again, it just became a static. You went from instruction 0 through instruction 127, and you were done. But as time went on, and Moore's law gave GPU designers more transistors, and as again, now they didn't ask for new modes. Now the game designer said, well, I really would like to have branches, and I really would like to do this and that. So basically, the ISAs, the instruction sets, became more and more general until they ended up being what they are today, which is fully general. You can do full loads and stores. You have 64-bit, 32-bit, integer, floating point, branching, looping. You can call functions. You can basically do almost everything exactly the same as you do on the GPU. For programming, the programmable on the graphics side is the only restriction is still where you get your data from and where you put it. This comes back to kind of the similar things I've talked about in CUDA, which is if you allow arbitrary writes, then if developers don't do the right thing, they will just write in the same location, and there's no order there, and the results will be different from board to board, from each time you call the game, and so that's still very much controlled, both for kind of correctness and simplicity of programming issues, and also just for performance. There's lots of kind of little restrictions which really help performance. So that's kind of how we went from fixed modes to very restricted instruction sets to kind of general purpose instruction sets. It was basically graphics itself, which is video games, professional applications. The developers just always wanted more. And so this happened basically over the last 10 years or so. And so if you kind of have looked at CPU history, basically GPUs went along a very similar path in evolving from fixed function calculators to very restricted kind of more general purpose to fully general purpose calculators. They just did it several decades after CPUs. And they did it faster because the GPU designers were aware of what the CPU designers had gone through several decades ahead. So they kind of, I think we've been down this road before. I kind of know what the next step is. We just need to figure out how to do it efficiently so that it doesn't break the bank. I seem to be ahead of my slides at any given point. So again, I've alluded to this. GPUs and graphics are parallel because they've chosen the right programming model and the right abstraction, which is programmer works on one element at a time, whether that's one pixel, one triangle, one vertex, it doesn't matter. Different stages, what that one element is, will differ, hence the naming, but it's always just one thing. And how they communicate and how they arbitrate things and how the ordering is done is all specified by the API. And those things would be serial, and they are to some extent serial, but there is pieces of the GPU which you only get to kind of use when you're in graphics, which make sure that those parts go really, really, really fast. All right? So it's not like that graphics has no bottlenecks, no things where you kind of need to look at everything and make some decisions, or at least wait for some things to complete in a certain order. There are. Else, you wouldn't get the kind of nice results that you do. It's just that those kind of little corners, those parts of the pipeline, the programmer doesn't have to worry about, the hardware designer has to worry about, and they basically spend a lot of time and effort making those things go faster and faster and faster. And so they haven't never become a bottleneck, and GPU designers are working very hard to make sure that that trend continues. So, and this kind of, so you can see kind of where some of the ideas for CUDA came from. Let the programmer work on one element, whether that's something in graphics or one thread at one time. Most of the time, you don't have to worry about what's going on around you, who came before you, who will come after you. And only when you really need to communicate, do you have to start thinking about that, how do you expose that, and stuff like that. Because CUDA is a general purpose programming model, that is exposed to the programmer. It's not like in graphics where you can have one fixed API, which while it has evolved, the skeleton of which has remained the same over the decades. It's actually a very nicely designed API, and so you can have fixed function hardware to handle that. If you have things where you need to communicate, where you need to have certain orders, ordering of your elements, stuff like that, you'll need to think about that in CUDA. But CUDA, unlike the graphics API, gives you methods of how threads can communicate and exchange data, primarily again the thread blocks and shared memory that we mentioned. And I should also point out something which, again, Jared alluded to the first time. So as I said, at some point, we had enough transistors to put all the functionality, wow, that white really doesn't come through, on a single chip. And you're saying, well, great, what do we do when Moore's law in 2 years' time gives us twice the number of transistors? For a CPU, because you only have a serial instruction stream, you need to make add more caches or invent new complicated out-of-order hardware. For a GPU, because the API inherently gives you all this parallelism, you can just say, well, I'm going to replicate those units which were the bottleneck. So, for example, pixel shaders were mostly the bottleneck. So you can just say, hey, I'm going to plop down 4 of them, leave the rest as is, and use up the extra transistors and give everybody more performance. I don't have to worry about making the GPU run faster. That's not what's inherently required to give you more performance. It's nice, but it's not required like it was for the CPUs for the last 40 years or so. And so this trend continues, and again, those units, those pipe stages which were bottlenecks at any given point, you could just replicate them. Note again, I'm not showing you, all the little units which deal with all the kind of little serial dependencies and bottlenecks, mostly because they really are tiny, and again, because they're really kind of hidden from the programmers. So the programmer's view is, I just magically get more boxes. Each box does the same thing, or a little bit more than the last generation. So great, I can do 2 times as much, 4 times as much, and so on. So in the end, you end up with this kind of generic floor plan of a chip full of little boxes, each of which is its own little core. And if you go back and look at the kind of Fermi kind of block diagram, you'll note it looks very similar. And that's basically because it is, at this point, the end point of that evolution, that basically, most of the units have been replicated, they have been unified so that each of those blocks can not just do one thing, actually they can do several things depending on what you just happen to need to do, because they're not general purpose, right? It's not that you have block A which can only do A stuff and block B which can only do B stuff. Because you now have general purpose APIs, the actual programmable parts, everything can do everything. So that's kind of why GPUs have, if you refer back to that graph Jared showed you the first time, been able to go and just add more and more gigaflops over time without having to completely reinvent themselves every couple of years, come up with a new execution paradigm, and just being able to scale with Moore's law. Right. And so something else, which we'll go into kind of in like lectures, well, probably 5 or so in more detail, but which I should mention is GPUs also take advantage of that they are doing the same thing over and over again. If you get 20 pixels from the same triangle, to calculate, the color, whatever it is, you're given a program, but it's going to be the same program for all of the pixels in that triangle. And the same thing is true for other parts of the pipeline. So, each of those throughput cores could basically have some control unit and actual kind of ALU, which is actual math, and they could all just be chugging away, independently. But for more efficiency, and because you know that you're going to be doing the same thing over and over again, what you can actually do is share the control part of the hardware between lots of ALUs, arithmetic units, and that means you can have pretty big savings. And here I'm showing, so okay, you can share them between 6, you can actually share them between a much larger number of kind of floating point units or ALUs and so on. And performance is still great because you're basically doing the same thing step by step by step, just on different pieces of data. Different pixels, different triangles, different vertices, what have you. And so they don't need to go off and do independent things too often. Actually, it's very rare. And you can kind of think of requirements of graphics, which again kind of influence this execution model which we have, which again Jared mentioned the first time, called SIMT, single instruction, multiple threads. So you have a single instruction which says, I'm going to do this for, assign this color to every pixel in a triangle, and you're going to work on it, and that instruction will work on all the pixels, or at least a big chunk of the pixel which make up a triangle, and you can just broadcast it out, and it still works beautifully. Now, if you have divergence, that is, everybody's doing slightly something different, then in this execution model, you suffer a performance penalty, but that's it. There's no the correctness, it's still correct, it's just a little bit slower. And so I said, well, you can share them over groups. So for NVIDIA GPUs, that group is called a warp, and it's 32 threads. So you can basically think of that 32 threads execute in lockstep as long as they're doing exactly the same thing. And if they want to do different things, then basically some part go off and do that while the others wait, and then the other side comes along and does what they want. But most of the time, they're all just executing nicely as a group, and you get the hardware benefits, which is less area, so it's cheaper. There's also less power, which is also good. And so all this performance, I mean, I said you evolve towards fully programmable general purpose instruction sets. You know, it wasn't until CUDA really came along that it was exposed in a nice way. But that didn't mean that people didn't want to take advantage of that. And I'm 5 minutes over, so I'm going to say, basically, there were lots of heroics early on to take advantage of that. And that kind of motivated, you know, the GPU developers, especially NVIDIA, to go back and think about, can we give people a real programming environment, a real programming language that they are familiar with to program, you know, to take advantage of all this hardware that we have, and hence CUDA. And with that, hopefully, I'm done. Any questions? Nope? Thank you for your time, and thank you for staying 5 minutes over.
For more, please visit us at stanford.edu.